In this lecture, we're going to discuss the von Neumann architecture in more detail. So up to this point, we have described each of the four main components that make up the von Neumann architecture. So let's just briefly review them real quick. So we have the memory, we have the input-output, we have the ALU, and we have the control unit. So now we're going to look at how we can put all these components together. The execution of a program on a computer proceeds in three distinct phases. We have the fetch phase, we have the decode phase, and we have the execute phase. Now, these three steps are just repeated for every single instruction, and we continue until we either get an instruction that says to halt, so until either the computer executes a halt instruction, or there is a fatal error that prevents it from continuing. So maybe an illegal opcode or a non-existent memory address or trying to divide by zero. Just trust me, don't try to divide by zero. Bad things happen when you do that. But we just keep repeating fetching, decoding, and executing until we either halt or we get an error. And this repetition is what we call the von Neumann cycle. During the fetch phase, the control unit gets the next instruction from memory and moves it into the instruction register. The fetch phase is the same for every instruction and consists of the following four steps. So first, we'll send the address in the program counter to the MAR register. We'll then initiate a fetch operation using the address in the MAR. The contents of that cell are placed then in the MDR itself. We'll then move the instruction in the MDR to the instruction register so that we're ready to decode it during the next phase. And then finally, we'll send the contents of the program counter to the incrementer and then put it back. So this points the program counter to the next instruction. So we're basically incremented by one. So what this means is the control unit now has the current instruction in the instruction register and has updated the program counter so that it'll correctly fetch the next instruction when the execution of this instruction is completed. So now it's ready to begin decoding and executing the current instruction. Decoding the instruction is pretty simple because all we need to do is just send the opcode portion of the instruction register to the instruction decoder. And this will determine the actual type of instruction. And then the instruction decoder will generate the proper control signals to activate the circuitry to carry out the instruction. So we just send the opcode over to the instruction decoder, and then it's going to figure out which instruction we're actually going to do. The specific actions that occur during the execution phase are different for each instruction because we may have different types of operations, so we're going to have different things that we're going to do based on what that operation is. Therefore, there's going to be a unique set of circuitry for each of the 2^k distinct instructions in the instruction set. And then the control unit circuitry will generate the necessary sequence of control signals and data transfer signals to the other units. So sending it to the ALU, the memory, and the I/O. And then when these signals are sent, they'll carry out the intent of the instructions. So what we're going to do now is take a look at a couple of examples to show what signals and transfers will take place during the execution phase of some of these instructions.